and position too, right? So we can use it for quite a few things. This one right here is just a, let's see how many slots we have in this encoder. Let's see. This guy's got 1, 2, 3, 4, 5, 6, 7, 8. So this guy's got 8 blades or 8 detectors in the encoder. So I don't know how the stethoscope turns out here. Once it loads in. Okay. Looks like it's gonna be, oh, that's upside down. And so it looks like we gotta do it like this. So this is the speed of the motor. So right now, this is an oscilloscope. If I had it, so oscilloscope. What's nice about an oscilloscope, and what's the difference between an oscilloscope and a meter, is a meter averages everything. So what you see when you look at a meter, you get an average. An oscilloscope shows you exactly what voltage is there, but the voltage it shows you is relative to time. So in the oscilloscope, not only can we measure voltage with it, we also can measure time. Okay, and of course, revolutions per minute is time, right? You understand that? So when I come over here and look at my scope, and I'm gonna blow it up real fast so we can see it. What we would do to measure this, and y'all that's at AC should know this, is wait a second, let me get it. What we're triggering at over here, because the motor is jumping a little bit, but we ought to get close enough anyway. So we'll move this down here so we can see it better. And then I got a cross right here. So normally what we do is we have the ability to adjust the position. And what we want to do is we want to measure time. So time is this way, and voltage is this way. So that means we have it on 1 volt per division. So 1, 2, 3, 4, about 4.8 volts. That's how high the pulses are. Okay. And then the time, I have it on, my time is 500 microseconds per division. So that means 2 divisions would be 1 millisecond, right? So that'd be 1 millisecond, 2 milliseconds, 3 milliseconds. This would be 3.5. So about 3.75 milliseconds. So how fast is the motor running? There's no such thing. So your car runs in milliseconds. Well, yeah, because motors are not rated in milliseconds. Motors are not rated in time. What is the speed of a motor is rated in what? This is the international standard. RPM. But remember, RPM is revolutions per minute. This is 3.75 what? Milliseconds. So what we have to do is we need to be able, from this encoder, we need to be able to go from time seconds, number one, from milliseconds all the way up to minutes, right? You understand? Okay. Come on, help me. First of all, I have eight slots in this encoder. So that means for every revolution, I'm getting 8 of these things. Right? You understand? So I want the time for one revolution. So if this is the time it takes for 8 of them, for one of them, how long is it going to take for 8 of them? So what would be the first thing I would do? Huh? I would multiply by 8. You can multiply the time or you can multiply the frequency. It doesn't make any difference whichever way you want to do it. So I take 3.75, right, times 10 to the minus third, right? And then I could multiply that by 8. And that gives me 30 milliseconds per revolution. What do I need to do now? Huh? Could do the reciprocal. Okay, so that would be, I could take the reciprocal of this. So that means I have 33.33 revolutions per second. We're still in seconds, right? You understand? I multiply this by 60. Good. So that motor is running at 2,000 revolutions per minute. So if we were going to bring this into a system, that's what we have to understand is that most of these encoders are going to be in what? It's not going to be in art revolutions per minute. It's going to be in revolutions per second. So the first thing I need to know is how many slots are in the encoder. Shut that for me. I know how many slots are in the encoder, right? You understand that? I would have to measure the time. About the only way I know you can measure the time is with an oscilloscope. Sure. Well, no. What we did is we measured the time between the pedals, and I know there's 8 pedals per revolution. Because if I was trying to get 8 of them up there, my scope would have worse resolution. So normally when we measure time on the oscilloscope, we try to get one cycle. Because the more information you try to put on the oscilloscope, the less accurate you're going to be. Y'all understand? Some of y'all do. So if my speedometer on my car, if I came over here, my speedometer on my car, if I come over here and here was 0 and right next to it was 120 and my thing was right there, how fast am I going? I have no idea. I just know I'm going somewhere between what. So what do we do on the speedometer? Well, we spread it out. So that means if I come over here and try to look at 8 of them like this, then that means my resolution for my scope is so small that it's going to be hard to measure. So what I do is I measure the time for one of them. So that would be one of them right there, right? You understand that? And what we came up with was 3.75 milliseconds for one of them, but I know there's 8 of them there. Okay, you understand? So this would be the time for one of them, but one of them is not one revolution. I get 8 of them for one revolution, right? You understand that? So I take this 3.75 milliseconds and I multiply by what? By 8. Now that would give me the time for one revolution, which comes up to be what? What's that? 3.75 times 3.75 milli times 8. It comes up, it gives me what? 30 milliseconds per revolution. Okay. Now what I got to do is I got to get time, my time over to a frequency, right? You understand? So what we would do is we got two options. I could go ahead and multiply this by 60, or I could come up, what we'll do is we'll take the reciprocal of that, and that gives us in a time into what we call a frequency, right? And this would give me the speed of the revolutions, which would be what? Or the time, yeah. I'm listening. What's that? 33.3, right? Okay. Okay, now that will give me the speed of the revolutions, but I gotta have revolutions what per minute. Then I'd multiply it. Yeah, so the 33.3 would be the revolutions per second because I took the reciprocal of seconds. So my answer is going to be in what? Seconds, right? You understand that? So the thing would be doing 33.3 revolutions per second. I multiply that by 60, and then that gives me the revolutions per minute. Because I counted them. Huh? Yeah, 8 pedals on the wheel. You know, so if we went over to the Fanuc robot, we'd probably have to get a magnifying glass to set. Now, what advantage does more pedals on the wheel have? Well, the more pedals on the wheel means that I can come up here and I can really slow this motor down, and I can still do the RPM, right? You understand? Because if I only had one pulse, then I'd only be counting one pulse per revolution, right? You understand? Now it'd be easier to calculate, but now my measurements wouldn't be near as accurate. So normally your encoders are going to have multiple wheels, multiple blades on them, and it depends on the resolution. How good do we want to make this? If I was going to use this for positioning in the motor, then the closer the wheels are, the better I can position it, right? Y'all understand that? So we can use incremental encoders for several different things. We can use it if we use multiple LEDs, we can determine direction, right? We can determine position. So if I wanted the motor to turn 350 degrees, if I knew the pedals, I could take 360 divided by the number of pedals, and that would give me the degree per pedal, right? So now I could turn the motor. I could start the motor at our origin and turn it so many pedals, and that would compensate. That would be so many degrees. So I carried up. I'll go and find some of the. I'll have to figure out what I did with them. The first robot that we actually got was a chain driver robot, college ball, years ago. That was one of those situations when they called me up and said, "Rich, we bought a robot. Come over and get it." So they just kind of handed it off to me. Of course, I had to learn how to use it myself. That's like these robots back here. They said, "Here, Rich, we got these robots. You're going to have to teach it." So, and we were talking about that technology that's been evolved since I've been here, and where I had to learn how to do it because never. So this was I brought this up because these are the kind of the questions that's on the Siemens certification test, just like this, right? It's got a lot of troubleshooting. Of course, our first test is going to be predominantly safety. So y'all that missed the first class, you better make sure you go back and look at that lecture and look at those PowerPoints, right? And then also symbols is the big thing on this test, and then being able to identify different sensors according to the application that are pictured in the test. Right now, what we're doing is we're working on function charts, and then after we do that, the next lab is going to be what? Yeah, the step charts, and we'll try to do it on your line. But when I realized the other night when I got home that some of these had some conditional statements that we haven't really talked about. So, and you'll run into that in most control systems where they have conditions. If it's true, it'll do what? It'll do one thing. If it's false, it'll do another. And we'll look at that when we get these done. So odds are, what we'll do when we get the function charts done, we'll bring up the actual documents and we'll look at the function charts for the actual lines, and then we'll come back and then we'll let y'all do the step charts, and then we'll come back over here and look at the true step charts for the two things. And then once we do those, of course, once we get an understanding, you understand things better instead of just using them. You understand them better if you do it yourself, right? And then when you go to the actual things, they make a lot more sense of why we do these things. Are we okay? Are you okay? So y'all ready to do some lab? All right, y'all know what we're working on, right? Okay.